Thank you. Setting the expectation high here. Okay. So thanks very much. I am honored to be here to tell you a bit about my work on low-rank optimization. Okay, so I want to begin by talking about what I mean when I say, large-scale low-rank optimization. So let's consider this problem here. So we're going to even have this phi function. We're going to let it be convex. And the point that we want to, the object that we want to study is really this factorization here. Okay, so you have this tall and skinny matrix U with, let's say a few columns, one or two columns, but it's very, very long, and we're taking the outer product and we're trying to optimize over this outer product, right? And so because of that, this function f of U is going to be non-convex. And moreover, it's going to be NP-hard. So you can encode many NP-hard, many difficult problems into this form. So this is why this is interesting. In general, you can't really solve it. And why we as statisticians and probabilists care about this problem is, well, in learning a lot of structure, when you're trying to learn an underlying latent variable, latent structure, oftentimes you naturally arrive at a problem in which you're trying to estimate a low-rank matrix here, like this UU transpose. And the point here is this would otherwise be a convex problem. Right? You're just doing a linear estimation here, perhaps with some regularizer, but the trouble here is because of this UU transpose, this object you're trying to estimate is non-convex, and that makes this whole problem not only non-convex, but even NP-hard. And okay, when I form the structure, a lot of people say, okay, I agree with you, I want to learn low-rank matrices, but my matrix is not positive semi-definite, and I say, okay, by the way, sorry, I should define my notation here. This inner product is just element-wise inner product here. So I tell you, if you want to learn a general matrix, a low-rank matrix, then you can factorize it as L times R transpose, okay? And okay, so you have this problem here, and I hope I can convince you that, in fact, you can rewrite it into this symmetric semi-definite form, right? So when we consider this as without loss of generality, you're just, in general, considering trying to learn a low-rank matrix. Okay? So that's one very important motivation for machine learning, statistics, probability, etc. Another one that's a little bit different flavor is the rank constraint semi-definite program. Okay, so this actually shows up in a lot of stats problems as well. Some of the famous results is both optimization stats, something like max cut, right? That this NP-hard problem could be solvable up to some limit using some statistical techniques, right? So we would solve a problem that would otherwise be convex, except for the fact that it is over this UU transpose. Yes, you have a linear objective, right? And then you have some constraint that's also linear. And if the constraint is not satisfied, then okay, this function will be infinite. So this is also encompassing all the constraint optimization problems. And you can verify this is non-smooth, but this is still convex, right? So it still fits within our framework here. So this class of problems broadly encompasses a lot of things, and it's generally NP-hard. And the reason that the community even cares about this problem is because some of the results that were developed in the 2010s, etc., when we discovered, okay, if we do a convex relaxation, right, that once we replace this UU transpose by the semi-definite matrix, that we get a convex problem that we can try to solve here. But okay, so this convex relaxation doesn't need to have any relationship with the original problem, right? So this could just be trivial. It just gets you a solution of 0 perhaps, and it's not super interesting. So actually the development was what I'm listing out as an assumption at the start, but this was kind of a major result that the relaxation would somehow be tight, and that the left side and the right side would actually be equal. There wouldn't just be just some bound, but that solving the convex problem would somehow solve the original non-convex problem. And the precise assumption is that when I solve this convex problem over the semi-definite matrix, that the rank of the solution is upper bounded by some R star that's less than or equal to my search rank R. And under this assumption, these two sides are equal, right? So in fact, because they're equal, this is not NP-hard anymore, of course, since you can now solve it. And when you go back to all these papers from 2010, all the way throughout the 2010s, you can see these problems like matrix sensing, matrix completion, phase retrieval, phase synchronization, orthogonal group synchronization, sensor network localization, they all have this flavor of establishing this, what we call as an assumption in this.
So for different problem, we expect a different threshold of this rank parameter R star.
So it might not necessarily be one, but we're just going to assume that it's less than or equal to R,
Okay.
because otherwise it's not quite equal. And I completely agree with you in that you have approximate rank conditions as well, but we're going to just ignore that detail for now. We're just going to take the simple case in which you have an exact relaxation. So I agree there's approximate relaxations as well, but let's just consider the exact case. Okay. So once these results were established, there was a lot of excitement from practitioners who thought that their problem, which can be put into this form, can finally be solved. Very exciting. And then they discover this problem has n squared variables that they absolutely have to optimize over. And that's very difficult. Whereas the original problem has only order n variables, and they just go ahead and they solve it anyway, right? And this is during the rise of machine learning, where you just do gradient descent, you see how well it does, and it does very well. Why is that, right? That's very strange. But because of that, right, you kind of had this landscape appear in which you have this two paradigms to solving this problem. You have the non-convex way, which is to just, you take your original problem and you just throw something like gradient descent and you just see what happens. And it's very fast. But okay, you might get to a local min. And you get this convex strategy, which because of all those theorems, you can prove it's globally optimal, but you have to optimize over n squared variables. And as a consequence, it's just completely, you cannot actually use it in practice. So what they discovered was actually that this non-convex strategy seems to work very, very well. To an extent that when I used to give this talk, people used to say, well, who cares? It seems like non-convex works anyway, right? But as a theorist, it's very unsatisfying that we don't know whether it's globally optimal or not, right? They say, well, is this really so bad? I need to convince you first that it is really bad. As theorists, it's kind of a fundamental problem that you don't know. You optimize, at the end, you still don't know. But for practitioners, I need to make a case why we care about global optimality. So I want to give you two kind of applications where it might be important. Okay, so one application is in operating an electric grid. Okay, so you end up with this problem here when you're trying to minimize the cost of electricity, subject to some reliability limits, like how much power I can generate, how much power I can transmit over a line, right? And you end up with this quadratic structure, and the reason is because you're trying to optimize, in the end, this vector of complex variables in which each one corresponds to a node in your electricity network. And it's a complex number because power sinusoidal, and then so you've got a magnitude and you have the phase, you have a voltage, and power is quadratic because voltage times impedance gets you current, and current times voltage. So it's quadratic. And the cost of electricity, for example, is kilowatts, kilowatt hour, like cents, etc. So it's going to be linear. So this is an optimization problem. And who cares about global optimality? Well, the power system is very, very large. It's very, very large. And so this problem is very, very big. And because it's very large, it's very important. You have lots of renewable energy, you have new things coming in. It's estimated that if you solve this suboptimally by order of 1%, that it costs the electricity consumer $1 billion. And so whenever I present this figure, I like to say, well, so maybe if you can improve this by 1% using whatever technique that you have, maybe you stand to get $1 billion of research funding, perhaps, right? So, okay, so there's a lot of room here to make progress, even though optimality it might be a small thing. For this application, in fact, it's even more dire because with the introduction of renewable energy, the grid is becoming harder and harder and harder to operate. And so when you actually talk to the operators in California, they'll tell you that I don't care about optimality. I can't really even solve this problem anymore because the situation is so bad. I'm just struggling to keep the lights on, right? So it's very important to be able to solve a low rank optimization problem, hopefully to global optimality.
What is the y-axis for the second picture of the curve?
Oh, this is the amount of load on the network. And what you see is that with the introduction of solar energy, right? So 2015, 2016, 2017, that the solar energy turns on during the day. and it offsets so much load that ends up, like the load then goes away. But then as the sun sets, then you get this humongous ramp.
Yeah.
And yeah, so they get a lot of issues here.
So the issue is then the difference between.
Absolutely, absolutely. Yeah, so actually estimating how bad this ramp is going to be at 5 o'clock today is a very important statistics problem that if you figure out, you can pay a lot of money, right? Because it's so important to make sure you have enough generation to be able to meet that. Okay, so this is one example. Another example is in estimating the phases. Okay, so here I'm showing you a kind of a cartoon of the electricity in Cleveland and West Michigan. Okay, so sinusoid, and it's the phase difference that causes power to flow between these two areas. Okay, but over the course of 300 miles, the actual phase difference is only something like 15 degrees. And you can imagine trying to measure 15 degrees across 300 miles. I mean, how would you do that? Would you run across and you measure? It's very difficult, right? So you might use some GPS timing. It's not so obvious. So how do they actually do it? How did they do it back in the day? Is what they did was they measured the amount of power transferred between these two nodes, right? They measured the power flows, and they solved an inverse problem, an estimation problem, right? Classic low-rank estimation problem in which your variable is that list of voltage phases where really you care about the phase, right? The magnitude you can measure, but the phase you cannot measure. And you're trying to estimate this outer product, okay, through measurements of the linear, right? The linear measurements of this outer product, right? So you get the structure just in this literal form in a real world application. And when you solve this incorrectly, you can knock out 55 million people from electricity, right? And lots of people lost their power, some people lost their life. So it's very, very important to be able to solve this correctly. So hopefully I made a case to you that when we solve these optimization problems, low-rank optimization problems, and you could have a local min, you could have a global min, right? And you run these algorithms, you really want to get to the global min, right? And you don't want your algorithm to just fail to converge. Even worse, you don't want it to converge to a spurious local min that tells you your system is in danger when it's not, right? You want it to be able to converge to the global min, the maximum likelihood estimation, right? Something that you can have a statistical guarantee. So in practice, it's also really important. Now, we can ask two questions here as theorists. The first question we can and should ask is, when does it fail, right? When does it converge to a spurious local min? Can we guarantee a priori based on our understanding of the problem that in fact this picture does not arise, right? And then for your particular problem, for some reason, it doesn't get stuck at a local min, and you always converge to the global min. It's non-convex. Is it possible to make a guarantee nevertheless, right? And this turns out to be very difficult, and it's a lot of work, which I will summarize a little bit later, but they require very strong, perhaps even heroic assumptions. And so a second question is, okay, maybe I can't make this guarantee, this a priori, before I make the estimation. Perhaps after I've made the estimation, I can try to check whether I've converged to the global min versus a spurious local min or failure to converge. Can I, after the fact, check whether I've converged to the global min? So these are sort of two different paradigms to the same problem, right? So these two questions, I'm going to present to you some results, some progress towards answering them. And the first line of work, which is really on when does non-convex converge to a global min, I want to tell you a little bit about my work on slight rank overparameterization. What does that mean? I'm going to tell you in a second. It's going to improve the landscape somehow. Okay, and so this is the paper there, and then we'll see that, okay, maybe it's conservative, maybe it's not, and we can try this different strategy of checking after the fact. It turns out it is possible to certify global optimality after you converge to it, and that's very exciting for people doing optimization. It's always very exciting that beyond just being able to solve a problem, that you can prove that you solved the problem after the fact. So I'll tell you how one might be able to do the second part here. How would one certify global optimality artifact? And this second work here is done with my student, Gavin, my collaborator, Salar Fatahi, at University of Michigan. And these are the two papers here. Okay, so let's begin with the first part here. Oh, and at the very end, if I have time, then I'll talk about some of my more recent results on actually applying this to some specific statistical settings and some of the results that I got. Okay, so let's begin with the first part here, which is this idea of improving the landscape. So what do we mean? How do you make a guarantee in a non-convex setting? So what we're hoping to achieve, right? The property we're hoping to establish is that this function here, which just doing an unconstrained optimization, we're just trying to find the bottom of this function here, that one of these three pictures arises, right? So either at a point, I look around and I see that the gradient is very large so that I can improve along the gradient so I'm not at a local min, okay? Or I'm at a point in which the gradient is equal to 0, but around me, there's sufficient curvature for me to make progress, to escape. And if neither conditions hold, then I'm somehow guaranteed to be globally optimal. So this is what we mean when we say that the landscape is somehow benign or it has no bad local min. So every local min is a global min. Okay, so this very unusual, very surprising structure is established in some of the machine learning literature. Okay, so let's just remind ourselves what the problem is, right? I have this phi in which it is convex. I was trying to solve a semi-definite program, and we consider this instead to optimize over this f of u here by substituting this UU transpose. Okay, and what we discover is that this property arises relating to the condition number. Okay? And so roughly speaking, it just means this convex function here, it is strongly convex, and its gradient is Lipschitz bounded. Okay, and actually we should consider the rank restricted version of this, but it's a little bit more complicated. So let's just consider the simple case here. And the results, all of the results here relied on the fact that for your particular problem, for some reason you collect enough samples and your condition number becomes somehow finite and converges towards 1 even, right? With the right statistical assumptions. And so, okay, and you have some value of the condition number, and they prove that if it's well conditioned enough, then this property arises. This particular generic problem here, okay, if this phi is just going to be well conditioned enough, then we're going to get the structure. You do not get stuck. It's no local min. All local min are global min. Okay, so it's very exciting. And immediately you say, well, okay, 1.5, that's a number. There exists some amount of samples for which this property will hold. And then the practitioner says, no, this is as much samples as I can have. I cannot get you any more samples. So it's then very natural for us to ask then, okay, can we push this 1.5 all the way out to maybe like 9, 10, whatever the practitioner wants to see. And we discover, unfortunately, that you can't just push it out very far. In fact, you can only push it out to a value of 3. And then there's a counterexample of 3. It's very disappointing because 3 to a practitioner as a condition number is almost the same thing as 1. A practitioner will tell you a condition number of 1,000 would be normal. 3 would be too idealistic. So what is this counterexamples? What does it say? Well, it doesn't say that we're going to fail. Right? I mean, empirically, okay, all kinds of condition numbers seem to not have local min, but you can't prove a worst case guarantee if there exists a counterexample, right? So this counterexample is not just a theoretical result. If you run a simulation on the counterexample, you will see that even with a condition number 3, okay, it is actually possible to not converge. Okay, and so I'm just showing 2 plots of SGD, it's just standard setting, and in one case somehow it decides to converge, and one it just stagnates forever. And when you run this over many trials, let's say 100 trials, you discover that, okay, a non-negligible amount of these would just fail and they won't converge. I'm not saying 100%, I'm not saying 99%, but having a a non-zero amount of failure, that's not good, right? It's not being able to know whether we failed or not is not good, Christian.
This is just for gradient-based methods, these results?
SGD.
Okay.
Just SGD, right? So maybe using a second order method, maybe it'll get something different. Okay. So it's very disappointing when you see this. And this is even just for rank 1, right? You're searching rank 1. In fact, this is rank 1 2x2 matrix. It's about as simple as you can make it. Rank 1 search for rank 1 ground truth, condition number 3, and you get stuck. Okay, so then when you take this result to a practitioner, what do you think a practitioner would do? Well, they will look at this and will say, well, have you tried setting the rank to be 2? And then you would say, why? I know it's rank 1, right? Why would I search for rank 2? And then the practitioner will say, oh, let me show you this plot here. I did a rank 2 search and I don't get stuck, right? So it's very, very strange that if I just increase the rank to 2 in search of a rank 1 ground truth, very counterintuitive. As theorists, we say, well, that's suboptimal. Why would you do that, right? Like, I mean, you already know what the rank is. But somehow, by increasing the rank, okay, then somehow you stop failing. So this case here, you know the ground truth is rank 1, you search at rank 1, it's exactly parameterized and you get stuck, but somehow by over-parameterizing, you're making it somehow worse in some sense, but then it doesn't get stuck. Question?
Thank you. So how about the initialization?
So this is random initialization, not even small random. I very carefully did not pick small random, arbitrary initialization.
Thank you.
Okay. Any other questions? Yeah. So initialization is a very good question because this can depend a lot. So this is arbitrary, large random initialization. Okay. And then even then it doesn't fail. So what's going on? Can we explain this? Can we explain this result? So I want to just mention now, like it's not super clear from the plot, but it also seems like it converges more slowly. So this is something that we need to examine a little bit later.
Is this linear?
Can we Google this? Oh, we're going to discuss this. Okay. Question.
Wondering is this linear convergence?
Is this linear? That's a great question. Is this linear convergence? We're going to leave that. Okay, we're going to leave that to part 2. But for now, let's just say, well, this one doesn't get stuck, right? It does converge. Actually converges more slowly. Okay. So we want to just explain that it doesn't get stuck. We don't know yet. We don't know yet like convergence rate. We just want to not get stuck. And there's been some work here, and this is sort of the result. It's actually very interesting, right? So what it says is that if I do get stuck at rank R, right? What does it mean to get stuck? So I converge to a point with gradient is equal to 0, and the Hessian is part of semi-definite. And I'm not too sure whether I've gotten stuck or not, but I've stopped at this point here. I can do something very interesting. I can add extra column to this U here. And so in doing so, if I start off with rank 1, this will make a rank 2. And also increase the rank here. So you can think about this F function, right? Like, so it will just be like a rank 2 expansion rather than a rank 1 expansion. But I can have a F with rank 2 as well, right? And kind of be the same thing. And we have one or two properties. One is either this U plus here is a strict saddle point. So you can escape it using just random perturbations of gradient ascent, etc. And if I cannot escape, then it's provably the global minimum. And because of this, we actually can also certify or guarantee. But this is something that will come back later. So this inability to escape when you add a column of zeros, okay, actually certifies the global optimality. And this is something that we're going to loop back to. But this also presents us with an algorithm, right? So we can increase the rank once we get stuck, add an extra 0, and it either will escape, or if it doesn't escape, then it's provably globally optimal. Okay? So you can imagine you just keep increasing the rank, and then this has been done in applications as well. For example, robot navigation, adversarial machine learning, we did that, right? It actually does really, really well in both settings. So in practice, it seems to work really well, but actually it's a very important point we have to make, which is that, well, if I keep increasing the rank, and at some point increase the rank to 1,000,000, then this will not be efficient anymore, right? So we actually need it to stop at some value that is far below n. And in practice, the reason it works so well is because by about rank 10, it succeeds, it doesn't escape anymore as globally optimal. But in order for this to be a guarantee that overparameterization gets you anything at all, you have to justify rigorously that you stop at rank, say rank 10, right? So of course, then people try to actually make this guarantee. Now this algorithm does work, but if the rank is too large, then maybe it's still not interesting. So let's just remember that we assume that there's an R star here, which is the upper bound on the rank of the solution here. So then when we set a search rank, the rank of the U that we're trying to look for, of course we could try to set it to be equal or less than R star, but that's not super interesting. That's something else, right? It could be NP hard. So we're going to focus on R is greater than or equal to R star, just sort of by assumption here. And what was proved, right, was that if you increase R all the way to equal to n, then it would be good, and you won't get stuck. And why is n a special number? Well, if you think about it, right, if you were n by n, then there would be no rank constraint anymore, right? So every semi-definite matrix could be factorized as an n by n matrix. So the geometry of the two sides then will always coincide. And since this is a convex problem and you can't get stuck, you can imagine why with n by n, this also doesn't get stuck. So it's not actually a super interesting result. It's actually somewhat basic. And okay, so n is also not interesting because, well, we could have just solved this as an n by n optimization problem, right? There's no need to do low rank. So low rank, right? In the real world, it succeeds with rank is equal to 10. Why does it succeed with a much smaller value? And then attempts to try to push it down, unfortunately, have encountered a very unhappy negative result. That, like this paper here, actually found a counterexample showing that not only can you get stuck at rank R is equal to 1 and R star is equal to 1, and I increase into rank 2, it seems to not get stuck, but there's another counterexample that rank 2 will get stuck all the way up to n minus 1. Okay? Up to n minus 1, there exists a counterexample which the search rank is n minus 1, and then your ground truth is 1, and you still get stuck. Okay, so it seems like, once again, we get the same picture, which is very sad, that empirically, it stops at 10, but in practice, I mean, for a worst case guarantee, you need R to be equal to n. You certainly cannot make a guarantee in a worst case setting. Okay, maybe you can do some statistical guarantee, smooth analysis, and that's where the field really went, right? So at this point, we see this picture that when you control for the condition number, you need the condition number to be almost perfect in order for you to make a guarantee. And otherwise, it seems like it works, but we can't make a guarantee in the worst case. And increasing the rank, it also seems like in practice, you just need to increase it a little bit, but in the worst case, you need up to n. And so the field, once it reached this point, it largely decided that, okay, probably we cannot make a guarantee under realistic setting. It's actually not possible. And there's some fundamental gap, and it's entirely possible there's some fundamental gap between theory and practice, right? Like a good example of optimization is the simplex method, which solves a linear program at exponential steps, in practice only linear steps. So there seems to be a gap between theoretically worst case and in practice is much better. So it seemed like theoretical worst case is just out of reach. It's not possible. And when I came to this problem, I had an observation. I asked, well, this result here, this condition number result, right? In which she said, if the condition number is really good, then you don't get stuck. Well, I asked, well, what rank do you need for this result to be true? What is the search rank associated with this result? Well, actually, they don't put any restriction on the search rank. It should just be any value. Any R is greater than or equal to R star, this result will be valid. And then I thought, well, what if I increase the rank all the way up to n? Then what is the condition number needed for there to not be any local min, right? And actually, the condition number guarantee doesn't, well, the rank guarantee doesn't care about the condition number, right? So it says if you increase the rank up to n, then any condition number, you're not going to have any spurious local. So you get these two pictures, and naturally you ask, is there something in between, right? Could it be that this condition number based guarantee that doesn't care about the rank at all could be improved by adding in rank, to mix the two ideas together to say, well, instead of just allowing any rank, maybe I need the rank to be slightly overparameterized. I'll force it to be slightly overparameterized. And that's going to increase my green bar a little bit more here, knowing that if I increase the rank all the way to n, then the green bar has to go out to infinity. So is it the case that if I increase the rank a little bit, improve the green bar just a little bit, right? And if I improve increase the rank enough from 20 to 40, maybe that's enough to cover my real world setting, and then I can make a guarantee. So that would be really good, but it could also be wishful thinking, right? It could also be the case that the picture stays like this all the way till suddenly you hit this and then it suddenly switches, right? So, I mean, really the question you want to ask is the effect of overparameterization smooth? Does it actually, smoothly transition between these two extremes, or does it abruptly go from here to here, right? And what I proved is actually that it is smooth if this condition number is just bounded. Okay, so this is a little bit hard to pass. So I'll tell you what the result actually says. So the result says that with a search rank, as we know, we don't want to set it to less than R star because, okay, that's not interesting. And we know for a fact that if it's greater than n, then you're guaranteed to not get stuck. So what this result says is you can increase the rank all the way up into, roughly speaking, kappa squared, where kappa is the condition number, and you could construct a counterexample. Kappa squared times R star, okay? But that is the last counterexample. And once you increase the rank past R star, kappa squared R star, then you have no more counterexamples and you're guaranteed to not get stuck. So that's to say, if I overparameterize just past kappa squared times R star, roughly speaking, then I'm guaranteed, okay, to not get stuck. So this if it's well conditioned, right, then at some point, the non-convexity becomes benign as you overparameterize. It's very important to see that if I treat the kappa as order 1 constant, then this is an order 1 overparameterization and not an order n, right? So that is really the main contribution here. And if you're not well conditioned, if your kappa is unbounded, then you get that picture from before, right? So you just will not be able to make a guarantee no matter what. So what does this imply here? Right? What it really implies is this particular sort of low rank estimation, you need a lot of ingredients here. Okay? If you only have well conditioning, you do not care about overparameterization, then you actually cannot make a very good guarantee. This result fills in the last gap here, but in some sense it's not super interesting, right? You actually can't make a guarantee. And if you overparameterize, but you don't have well conditioning, like a lot of the prior result, right? You can't make a very good worst case guarantee. And there's some stuff here on smooth analysis, right? But the worst case is not very good. And this is really known. So you can improve on this by mixing the two ingredients together. Now, how did I prove this result? So the proof technique is to argue about counterexamples, the inexistence of counterexamples. So consider this statement here. If R over R star is greater than or equal to 10, overparameterization by a factor of 10, then you don't get stuck. And I make this claim, and let's say, okay, you don't agree, and I put this up on archive, and you want to take this archive down. You would try to look for a counterexample, right? You try to look for a way of refuting this statement. Well, what would that look like? Well, you need to find a phi that's a counterexample, right? And this phi has to satisfy some conditions. The first one is that you can state some U bad for which it has no gradient, is Hessian semi-definite, and it doesn't recover your U star has to be the solution to this convex optimization problem, as rank needs to be bounded by R star and needs to be overparameterized by a factor of 10. Okay, so this is really a feasibility problem that you're trying to solve here. And if you find such a choice, then the statement is false, right? I have to retract this statement. So if you try and you cannot succeed, then you have to accept that the statement is true. Okay, so that's sort of the basic idea of how do you prove this result, right? It's to look for possible counterexamples and argue that they don't exist. And the key insight to even begin to attack this is the realization that actually the search for this counterexample could be a convex program, a convex semi-definite program, if I fix the U bad and the U star. And since it's convex, then there's some strategies you can try and solve it. Okay, so then you can also solve it numerically, and you can just see what happens. Now, if the condition number is really good, then it's really known that you don't get stuck. So when you just construct a counterexample using some U bad and some U star, you're going to see, okay, you just construct some U bad that is the engineered bad local min, and the U star is the global min. Then you're going to see that the condition number cannot be good. Because if the condition number were good, then you can't get stuck, or you end up contradicting a known theorem that's already been proven, right? So your condition number has to be bad. So the actual strategy for proving this theorem is to exhaust all the possible choices of U star and U bad. And then all the U bad will have to be, n by R, and all the U star will additionally have to have the rank constraint to be R star. And they have to not recover each other. So U bad transpose must not equal to U star transpose. So you exhaust all the choices, and there has to be a boundary, right? Has to be a boundary because at some point there's no more counterexamples. So the critical thing is to find where the boundary is. And it turns out the boundary is this very, very nice number here, 1 plus 2 square root of R over R star. And what does that mean? It means your real world problem, okay, so the overparameterized counterexamples are ill conditioned. So your real problem has a condition number of kappa, right? It's just some value. And then what I can do is I can increase the overparameterization ratio R over R star to increase the boundary until it covers my fixed kappa, right? And once it goes past it, then there's no more counterexample to disprove my particular value of kappa. Okay, and then you can rearrange that a little bit, and you're going to get that if I increase R over R star greater than 1 over 4 kappa minus 1 squared, then you have no more counterexamples. Okay, so that is the outline of the proof. Okay, normally people are very interested that you could even pose the search for counterexample as a convex problem at all. So I just want to very quickly sketch out how that might be possible. Okay, so it is possible. Like if you just consider the quadratic case here, really the key thing that you have to realize is that it's quadratic with respect to this A, but it's going to be linear with respect to this A transpose A. So if you compute the gradient, well, the gradient is this horrible thing here, but it's going to also be quadratic with respect to A and linear with respect to A transpose A. So this condition for the gradient to be 0 is in fact a linear condition on this A transpose A, right? And then now you think about the semi-definite Hessian, right? There's a horrible expression here saying that the Hessian is semi-definite at this U bad here. But you notice that once again, it's linear with respect to this A transpose A component. And so this is a semi-definite condition over, it's a linear matrix inequality over A transpose A. And finally, you can impose a condition number constraint. This is also convex, right? So you can see that this is in fact convex. So as a sketch for quadratic, in practice, you'd have to do some more stuff to optimize over the gradient and the Hessian of the phi, but you can see how it might be possible with a fixed U bad and U star, right? But what's the problem? Is you can solve this, you can find a counterexample, but then you have to optimize over all the U bad and all the U star somehow. I can do it using a computer, no problems, right? But I can find a counterexample. I cannot disprove the existence of a counterexample by optimizing over all of these. So it took a long time, right, between being able to formulate this and actually proving this result. And it took 2 extra steps, both very difficult, right? The first is to construct a lower bound on that line that we wanted to construct, right? The key thing about this lower bound is not all the details are not interesting, but that it contains only 2 parameters, alpha and beta. They're horrible functions of u bat and u star, which I won't even spell out for you because it's very messy and it doesn't tell us anything. And they're actually very simple parameters that just go between 0 and 1, and this beta is just non-negative. So, okay, so one thing we could try is to just optimize over alpha and beta, maybe we get a lower bound and that's it. So unfortunately, right, so while it reduces, the number of parameters from n r plus r star down to 2, if you just optimize over this, then you get a trivial lower bound and it's not interesting. So then it took a lot of work to figure out that these alpha and beta are not just arbitrary, that they obey a particular inequality, they're somehow correlated. And so once I figured this thing out, it became a very simple problem of optimizing this gamma alpha beta with respect to this constraint here. It becomes a high school problem. And you can show that this is true. And that's how you prove this result. Okay? And in the end, we end up with this condition here in which, right? So that past this point of roughly speaking kappa squared times r star, there are no more counterexamples, and you're guaranteed to have no spurious local limit. And then moreover, you need to construct the counterexample, and I won't go through the details of that with you here. So this is quite conservative. When you show this to practitioners, they're not so happy to see this kappa squared. They'll say, my problem, my kappa is 1,000, and this is 1,000,000. So do you want to do 1,000,000 by whatever, right? This is not good. But this is also conservative, right? There might be some strategies to bring in some of the smooth analysis into this particular proof, and maybe you can make some progress here. I'm not too sure, right? But it's still, real problems, this guarantee might not hold. This principle that overparameterization might make it better might be true, but in the worst case, you can't make a guarantee. A priori seems to be fundamentally quite conservative, even once we made so much progress, right? So I want to tell you the second part here, which is, okay, so if I can't really make an a priori guarantee, can I at least verify convergence after the fact? Okay. And the key weapon is this proposition that we introduced halfway through the last part here, right? That if I increase the rank, then it's either a strict saddle point in which I can escape, or it's guaranteed to be globally optimal. Okay, so that inability to escape certifies global optimality, and if you just go through the proof of that and just rearrange some terms, you can make this guarantee. What that says is if I'm approximately, second order optimal, right? My gradient is almost equal to 0. My Hessian is almost a positive semi-definite, and if I'm rank constrained, then if I have extra column zeros, for example, they're actually guaranteed to be near globally optimal. Okay. So if these numbers are 0, you can see then this is 0. Okay, so we can just use the semi-definiteness of this, right, and the lack of gradient if it's also rank constrained. So actually, if I just converge to a rank deficient second order point, then I'm done. And here I just briefly pointed out that when I increase rank 2, and if I converge, it has to be rank deficient, right? So seems like then we're guaranteed to get certifiably globally optimal. Then what's the problem? So then you see here, actually, if you squint, it's that this thing here converges very quickly, right? But, right, Xiaohui asked, is this linear convergence? So this is a linear plot. And if you look at the log plot, it looks like this. Okay, so it's very disappointing. You get this very weird structure in which, okay, if you're exactly parameterized, then your convergence is linear, very, very fast. But then if you're over-parameterized, your convergence is not linear anymore, but sublinear. Yeah, so in fact, it comes with a trade-off. Even though you can escape more often, your convergence behavior gets much, much worse. And so you can't really, it seems like you can't get both at the same time. And whereas here you get linear convergence, when you over-parameterize, you become sublinear in practice. So because you're sublinear, you still can't get second order optimality very easily. You can't actually get certified global optimality. Okay, and it's very weird why this happens. So I want to draw you this little picture here. Okay, so this is the manifold of fixed rank matrices, rank R. Okay, so we have two ways of writing it. You can write it like this here, in which your matrix is rank R, but right, seeing that as an open set, right, it's not a closed set. It's very, if you rewrite it in this form here, right, where U transpose, then you need that U to be full rank, and you can see now this is actually not a closed set. So it doesn't contain the boundary, right? In order for this to be a manifold, it cannot contain the boundary. And now when you're exactly parameterized, and then you try to converge to a point, right, you're always converging to some point in the interior. But when you're overparameterized and you converge, you're always converging to a point on the boundary. And the trouble with this manifold is that the curvature gets more and more and more extreme as you get closer and closer to the boundary. And at the boundary, the curvature becomes infinite. And many of the statistical guarantees break down, many of the algorithmic guarantees break down, a lot of things break down. So it's a very ugly regime to be in algorithmically. And you can actually quite easily show something like gradient descent, in which you're going in here and then you just subtract the gradient and you see what happens. It actually has a convergence rate that's dependent on this condition number here, which is actually correlated with the curvature of the manifold, okay? And what you see is if you converge to a point in the interior, very far in the interior, and the convergence rate is really good. As you converge to a point closer to the boundary in which the condition number is bad, your condition number slows down, but still linear. And yeah, if you're converging towards a point on the boundary, then you don't want to ever get there because the convergence rate just gets slower and slower and slower and slower and slower. Okay, so I don't want to tell you exactly, because I don't have enough time. I don't have time to tell you exactly how to overcome it, why it overcomes it, but I can tell you how to overcome it, which is actually what we did was we added a simple preconditioner here with a U transpose U and this regularizer here, this kind of this ridge regression. And it turns out when you just add this term, right, which by the way, doesn't increase your cost, right? It's actually, right, N is very large, R is very, very small. And so inverting this very small matrix is very cheap, R to the 3. This requires R squared memory, right? Applying as N times R squared, that, right, when the condition number is good, it converges quickly, right? When the condition number is bad, it converges quickly, but critically, as you converge to the boundary, it still converges linearly. So this algorithm is able to be immune to the ill conditioning and rank deficiency. Okay, and so some of the previous work here is something called scale GD. Some of you might be familiar with this. And what it does is it preconditions by just this U transpose U here, and there's some underlying reason that's related to the Riemannian metric on this particular manifold, and indeed, when the condition number is finite, when you're converging to a point on the manifold, it works. But when you're converging to the boundary, then it's going to fail. Okay, so really this regularizer is what is necessary to be able to prove a linear convergence rate even as you converge to the boundary.
The rate of convergence depends on how you choose the parameter of the preconditioning.
So you basically you decay it.
So
right?
it's
a geometric decay. And then the convergence rate then becomes tied down to this beta. So it actually is beta, right? Okay. Yeah. So I'm not going to prove this to you because I do not have time to prove it to you. To just tell you the theoretical guarantee in the bounded condition number case is it converges according to beta, right? So then if you combine this with part 1 here as a theoretical guarantee, it just means that starting from arbitrary possible initial point, you could get there in like log number of iterations, or whatever your iteration cost, that's what it is. Okay. And so that then you get an end-to-end guarantee this way. Okay. So that's these two papers. I had some further work, right, in the statistical side. So that result that I presented for bounded condition number, I have actually extended to RAP rank restriction here. let me just go through really quick, right? So RIP is like this bounded condition number, but you're restricting it to matrices of bounded rank. And the condition number is actually 1 plus delta divided by 1 minus delta. It's something a little bit different, but the guarantee turns out you can make a stronger guarantee in which you allow the gradient to not be 0, but some finite value. You can allow the Hessian to be not perfectly semi-definite. And what the important thing here is that if you let epsilon2, epsilon1 be 0, but you allow a noise perturbation, then you end up with this term here, which you can prove as minimax optimal. So you can actually substitute some of the existing results. You can show that you get a minimax optimal recovery, and you can apply this to the asymmetric case, and you get a minimax optimal recovery as well. And moreover, this preg GD, then you can show that you end up also converging eventually to a minimax optimal recovery. So for me, this result was quite strange, because if I think about it, because of the ill conditioning and you're going to the boundary, when you add a noise, it should be quite scary, because you're inverting a near singular matrix onto noise, right? You shouldn't succeed, but actually it turns out to be stable, and you can show that the error doesn't blow up because of some perfect cancellation, both in theory and in practice. Okay, so with that, I want to end the talk. Right, so this is the 2 main papers, and I'm going to thank my sponsors. Happy to take any questions.